So hello guys, a big welcome to the Manja's Electro Hive channel, where we talk electronics, tech and tech advancements here in Uganda. I'm Joseph Okling, a biomedical engineering student at Macquarie University, and today I'm going to be taking you guys through resonance in LC circuits. So today we're going to have a wide look at this. It's going to be a brief one actually. We're going to look at how RLC circuits work at the resonant frequencies. So we find that when you apply a sinusoidal voltage at a resonant frequency to this LC circuits, you find that they behave in a very interestingly weird way. So let's take for example this. Let's take for example the series LC circuit. So here you find that when you apply a sinusoidal voltage to these two elements in series, you find that the impedance is zero. At the resonant frequency, the impedance is zero, and hence it behaves as a short circuit. Therefore, the current flowing is maximum, as you can see here. Then for the parallel LC circuit, when you apply a sinusoidal voltage, the equivalent impedance of these two elements is infinity. And you know that when impedance is infinity, that element is going to behave as an open circuit, since there will be no current that will be able to flow through that infinite impedance. So this, when you apply a sinusoidal voltage at resonant frequency to this parallel LC circuit, you find that it behaves as an open circuit, and hence the current cannot flow from the source to the ground. Here a maximum current flows from the source to the ground, since the equivalent impedance of these two elements becomes zero at resonant frequency. So let's have a look, a theoretical proof to show why these two circuits are behaving the ways they do. So for the series LC circuit, let's find the equivalent resistance of these two elements. So let's say the impedance of the inductor is ZL and the impedance of the capacitor is ZC. So Z equivalent is the same as for series impedance connections. We just add their impedances. So we're going to say ZL plus ZC. We know that ZL is equal to J omega L plus J. Let me reduce the size of this. So this will be 1 out of J omega C. That's the impedance of a capacitor. So if we took this up, minus J out of omega C, so you can pull out J, Z equivalent equals to J omega L minus 1 over omega C. So that's the equivalent. So what value of omega, the angular frequency? So our F naught, let's say F naught will represent the resonant frequency. By the way, I'm sorry for the background noise outside, since some people are building something or whatever. But let's proceed. And so here omega naught equals to the angular resonant frequency. What's the relation between omega naught and okay, let's first write this 1 over LC. That is, omega naught is equals to 1 over the root of LC. That is for an LC circuit, but then omega naught is just the same as 2 pi F naught as well. So that's a relation between our resonant frequency and our angular resonant frequency. So at what value of our angular frequency does our impedance become zero? It's at when our angular frequency is equals to omega naught, which is just the same as resonant frequency. So this will be equivalent to 0. So when our impedance here, equivalent impedance of these two is 0, we have behaves as a short circuit, and the current flowing will be maximum here. So if we were to just theoretically analyze this circuit, we would as well see that for at resonant frequency, there's going to be the voltage drops across these two elements is going to be the same, but opposite in direction, opposite in phase direction. So you're going to find that the voltage drop across the inductor will be V plus, and the voltage drop across the capacitor will be V minus, since they are opposite in phase. So when you add up these voltage drops here, the equivalent voltage drop V plus V minus, it will give you 0. Since it will give you 0, and since our voltage is 0, remember voltage is what you need to push electrons across a certain hill, which we can call as resistance. So if there's no resistance, or for this case impedance, so if our voltage V equivalent is 0, our impedance equivalent is 0, and that means there's a maximum current that is going to be flowing at that particular point. So from this, after obtaining our Z equivalent as 0, so we have an equation here, Ohm's law. You can use Ohm's law, V equals to IR, where R is the impedance for this case. So making either subject, this is for AC, since we're using AC, the current changes with time. Then you have the equivalent resistance is 0, our equivalent impedance is 0. So you find that our current is going to be infinity. But you know that in real life the current does not reach infinity, because the internal resistance and limited output source current take care of that. So you can't have an infinite amount of current in real life. Now here they're saying, if you do not like equations, just think that at resonant frequencies, the voltage across the capacitor and inductor are equal and opposite in phase. So that was what I was explaining last time. Effective voltage drops across the series pair is 0, the equivalent voltage drop, since the voltage drops will be equal but opposite in phase. So when you add it up, they'll cancel out, so the impedance will be 0. So let's have a look at the parallel LC circuit and why its impedance is infinite, because for this its impedance is infinite and acts as an open circuit. So let's find the equivalent for the parallel parallel LC circuit. Equivalent resistance or equivalent impedance of two elements in parallel is the same as the product over the sum. Also, so since we have here L and C, so we're going to have ZL, impedance of the inductor, times the impedance of the capacitor, impedance of the inductor plus impedance of the capacitor. So what is this? It's J omega L times 1 over J omega C. And so for this one, it will be J omega L plus 1 over J omega C. So we see that the J omega and the J omega cancel in the numerator, so we shall remain with L over C divided by J omega L minus 1 over omega C. So now if we pulled out the negative here to attach the J such that we can take it up, we shall just have, and we can as well just bring this down. So if we said negative j, say 1 over LC, here we shall have 1 over omega c minus omega L. Remember, I've multiplied the inside part by a negative and pulled it out. Yeah, so you can take the j up. If you multiply the LC inside, you shall see that you shall get here we shall get what? Sorry, when we bring this down, it becomes c over L. It's the reciprocal. So the c's cancel out, so you have 1 over omega L minus this times this will give you omega c. So that is our equivalent impedance. So if we inserted our angular frequency equal to the resonant angular frequency, our Z equivalent will be equal to J over 0, which is just the same as infinity. So after obtaining that, which this equation here is this, by the way, so our IT from Ohm's law will be equal to what? 0. The current flowing will be equal to 0, and hence it behaves as an open circuit. So for this case as well, if you do not like equations, consider the following. Consider the following. At resonance, you know that the impedance and voltage across L are equal in magnitude but opposite in phase with respect to C. So that is true. That is the same thing realized from the first statement up there. From this, you can infer that an equal but opposite current will flow through L and C. In other words, at one moment, a current is flowing upward through L and downward through C. The current through L runs into the top of C, while the current from C runs into the bottom of the inductor. At another moment, the directions of currents reverse. Energy is bounced back. Energy is bounced back in the other direction, and this behaves as an oscillator pair. So basically what they're trying to mean is, when you have your, let me just write here. So you have an AC source supply, you have your inductor here, have your capacitor here grounded. So at one point you'll have a current flowing here. This is L, then this is C, IL. Then there will be a current IC here. We shall have a supply current I in here. So at resonant frequency, we shall have a current flowing from this side, current flowing from here, this side, and here, this side. This happens as a result of the capacitor charging up while the inductor is discharging, and the inductor charging up as the capacitor is discharging. Here you need to understand the basic concepts of a capacitor resisting a sudden change in an instantaneous change in voltage, and an inductor resisting an instantaneous change in current. In that, if the capacitor is discharging, remember the capacitor discharges current very fast, so the inductor tries to oppose that very fast discharge of current or change in current as it is charging up. So after the inductor after the capacitor is discharged, the inductor is charged. So as it is discharging, the capacitor as well will be resisting the change in voltage from the inductor. So that is the basic concept of operation of an oscillator here. So here they talk about energy is bounced back in the other direction, so it will keep switching. So this time you find that your inductor current is going up and the capacitor current is going down. In the next cycle it will be going down as this one here is going up. So during this process, this current here is 0. We shall get to know why. So here they say that this internal current flow around the LC loop is referred to as a circulating current. Now, as this is going on, no current will be supplied through the network by the power supply. So this current will be 0. No current will be supplied by the power supply because the power source cannot feel a potential difference across the network. So another way to put this would be to say that if an external current were to be supplied through the LC network, it would mean that one of the elements, L or C, would have to be passing more current than the other. However, at resonant frequency, this does not happen because L and C currents are equal and pointing in opposite directions, which is this statement here validates the fact that they say that at resonance, you know that the impedance and voltage across L are equal in magnitude but opposite in phase direction in C, which is also just the same as one that was mentioned up here. So that is the basic operation of resonance in LC circuits. So thank you guys for following through this video. I hope you've learned something, and if you feel like the content wasn't really worth it, you can please give the video a dislike, and please drop your comments down in the comment section so I can be able to learn what I probably need to change about my approach of giving out, over teaching or discussing with you guys. I hope to meet you guys in the next video. Best up.